If you took a high school linear algebra class, you likely spent hours memorizing this specific formula, AD minus BC. It is the determinant, and for most students, it exists only as a rote arithmetic rule with no clear connection to the real world. But in computer science and machine learning, this number is far more than a calculation. It is a physical diagnostic tool used to monitor how data is being reshaped inside an algorithm. To actually see what that looks like, we have to view a matrix as a verb. It is a transformation, an action that takes a space and warps, stretches, or compresses it. Imagine a standard two-dimensional grid. At the origin, we have two basis vectors, at I and at j, which form a simple 1x1 square. This is our unit square, and its area is exactly 1. When we apply a matrix transformation, the determinant acts as a scaling factor. It measures exactly how much that unit square's area has changed. By tracking this single number, we can quantify exactly how a mathematical operation has expanded or shrunk the area of our coordinate plane. Consider the first state, expansion. When the determinant is greater than 1, vectors stretch the unit square into a larger parallelogram. Now, during a shear transformation, the vectors slant the shape, but the area counter remains exactly 1. The space is identical. This happens because the algebraic formula, AD minus BC, is actually a geometric calculation of physical area. We can prove this by drawing a bounding box around our slanted parallelogram. Subtracting the area of the extra triangles and rectangles outside the parallelogram leaves a specific remainder. That central area is the exact result of the AD minus BC calculation. The math isn't just a set of symbols, it's a direct measurement of how much a 2D grid has been stretched. When the determinant is a fraction between 0 and 1, the vectors push inward. This is compression, where the space is packed into a fraction of its original size. But what happens to the orientation of these vectors if the determinant drops into negative numbers? A negative determinant signifies an inversion. Our I-hat vector crosses over the j-hat vector, effectively flipping the orientation of the space. It's the geometric equivalent of turning a piece of paper over to its reverse side. The area exists, but the coordinate system's handedness is swapped. In this state, the transformation hasn't just scaled the data, it has turned the entire orientation of the grid inside out. This leads to a critical threshold, the moment the determinant reaches exactly 0. Physically, this means the vectors are squished until they land on the same line. Our two-dimensional area has been crushed into a one-dimensional space. At this point, the area of the unit square is 0. Geometrically, it has been eradicated. This dimensional collapse is more than just a geometric quirk. It represents a permanent loss of information. In machine learning, this is why the determinant is so closely monitored. As this technical breakdown of the Hessian matrix shows, the determinant is used to evaluate model evidence and verify if the data logic is surviving the training process. If that determinant hits 0, the mapping becomes impossible to reverse. Because a whole dimension has vanished, you can no longer work backward to find where your original data point started. This makes the geometric transformation completely irreversible. The original mathematical relationships between data points are permanently flattened and destroyed. Ultimately, the determinant serves as a diagnostic tool, signaling whether an algorithm is successfully processing information or if its internal logic has permanently collapsed.